Hello, Narayan sir.
Yes,
Good afternoon, sir.
good afternoon.
So this is Dr. Halda Sharma from Medicaps University.
हम्म
सर मॉर्निंग में आपका सेशन अटेंड करा, बहुत ही अच्छा लगा, बहुत अच्छी बातें बताई आपने। मैं एक पूछना चाहता हूँ सर मैं कि अगर सेम थिंग अगर हम एक्सेल में करें तो उसमें क्या प्रॉब्लम आती है, उसमें क्या डिफरेंस है दोनों के रिजल्ट्स में?
नहीं, कोई डिफरेंस नहीं है, पर जो आप जो कुछ कुछ चीजें हम बताएंगे, ओके, वो एक्सेल में नहीं होती। फॉर एग्जांपल, अगर आप विल्क शपीरो टेस्ट करना चाहें एक्सेल में, तो उसका ऑप्शन नहीं है, आपको एडिन वगैरह कहीं से इंस्टॉल करने पड़ेंगे।
हाँ, एडिन से होते हैं, बिल्कुल सही कहा सर आपने, एडिन से हो जाते हैं।
हाँ, तो वो पर ये कि फिर आपको हर चीज के एडिन भी नहीं मिलेंगे, जैसे
हर चीज का नहीं मिलेगा। हाँ
ब्रूस गॉडफ्रे टेस्ट वगैरह या कुछ कुछ और हैं, तो उस
हाँ।
चीज के नहीं मिल पाएंगे, वो सिर्फ स्पेशलाइज सॉफ्टवेयर में ही होते हैं।
अच्छा,
तो
तो सर
वो है।
स्टेटा का कौन सा वर्जन यूज करना चाहिए सर?
मैं अगर वो डिपेंड करता है, अगर आप बेसिक काम ही कर रहे हैं तो वो तो स्टेटा के किसी भी वर्जन में हो जाएगा, वो
तो आप
कोई
अभी
इशू
बता रहे हैं ये किस वर्जन में होगा?
नहीं। ये तो अभी 16 है, ट्रायल वर्जन ही है,
अच्छा
1 मंथ
सर,
के लिए।
इसकी क्या आप कोई लिंक शेयर कर देंगे सर, जिससे कि हम उसको डाउनलोड कर सकें उसी वर्जन को?
मैं कर देता हूँ, लिंक शेयर कर देता हूँ।
तो क्या होगा, हम उसी वर्जन को डाउनलोड कर लेंगे सर ना?
ठीक है।
थैंक यू सर, थैंक यू वेरी मच सर।
ओके।
हेलो सर, एक बात और पूछनी थी।
हाँ जी, हाँ।
तो मुझे आपका मोबाइल नंबर बताएंगे सर?
मोबाइल नंबर आई पुट इट इन द चैट बॉक्स, लास्ट में शेयर कर देता हूँ मैं।
बिल्कुल ठीक सर। थैंक यू सर, थैंक यू वेरी मच सर।
ओके।
ओके।
If anyone else has any query, okay, I can take up that. Any question, any doubt to anyone?
Naren sir, shall we start the session?
Sure, definitely.
Okay, so welcome all participants. In the first part of this session, we have discussed about the linear regression and we have discussed about the basic concept of regression with the help of support of Stata. And in this particular session, I think sir is going to discuss about multiple regression along with the Stata and many more examples. Over to you, sir. Thank you.
Thank you. Okay, so let's continue with some of assumptions, okay, which you are also going to encounter them, okay, quite often in your data analysis. There is an assumption of the homosedasticity. There is an assumption of autocorrelation. These are the two primary assumptions which are being hit when you indulge into a data analysis. When you have a cross-sectional data analysis, okay, which basically means that you are taking data across, okay, the various observation units. Okay, for example, okay, just let me take an example that among all these participants, okay, what I want is what is their monthly income and what is their monthly spending, what is their consumption level. Okay, so participant number one, okay, what is the monthly income, what is the consumption? Participant number two, income and consumption. Participant number three, okay, income and consumption. If I'm taking a data in this format, okay, so among all these participants of this program, okay, so I take their income data and their spending data. This is what is my typical cross-sectional data set. You can, okay, you can also have a time series data set, where in this case, okay, what I'm taking is a data of, let's say, income and consumption, but okay, on one cross-sectional unit at a time. Okay, so for example, my consumption, okay, my monthly income, okay, from the year 2000, okay, so 2001, 2002, 2003, what was my consumption and monthly income and monthly consumption, monthly income, monthly consumption, okay, for all this period, okay, or yearly income, yearly consumption, because I'm collecting data on year-to-year basis. So 2000, 2001, 2002, 3, 4, 5, 6, okay, and so on till 2020. What was my annual income? What was my consumption? So if I collect my data in this way, this is my time series data. When you have a cross-sectional data, and then you can also put them together. Participant number 1, okay, year 2000 and 2001, okay, what is the income and consumption? Participant number 2, year 2000, then you 2001, what is the income and consumption? This way, if I collect data, that becomes my panel data. So you have cross-sectional data, you have time series data, and you have a panel data set. So when you have a cross-sectional data set, okay, there is generally the one assumption which gets violated quite often, which is the assumption of homosedasticity. Okay, so time series generally suffers. Sorry, cross-sectional data set generally suffers from the notion called heterozygosity, and the assumption is that of a homosedasticity. Homo means same, and sedasticity means variation. So same variance. That's an assumption. So this assumption generally get violated in a cross-sectional setting. And in the time series data set, okay, generally the assumption which gets violated is the assumption of no autocorrelation. Okay, so these are the two assumptions which I'm also going to talk about. So time series generally suffers from the problem of autocorrelation, while the cross-sectional data set generally suffers from the, okay, mostly, not, okay, almost in more than 90% cases, okay, you have the cross-sectional data set suffering from the heterozygosity, and while time series data set suffers from the autocorrelation. Okay, it doesn't mean that time series does not have heterozygosity. Time series also, okay, most of the financial time series also suffers from heterozygosity as well. So there is a joint problem, okay, in the case of some of the time series. But if you talk about in terms of the majority of the cases, cross-sectional data set generally suffers from the violation of assumption of homozygosity, while time series, okay, data set generally suffers from the assumption of no autocorrelation in the time series, okay, data set. And in the panel, okay, you generally have both these assumptions being, okay, violated quite often a case. Okay, so let me now talk about the assumption number 3, which is the assumption of homosedasticity. Okay, or the violation is that the variance of the error term, okay, is not constant. Okay, if it is constant, okay, that's perfectly fine. That's what you wish. That's what you are expecting. Okay, that's what was the assumption. Okay, but if this is not the case, okay, then you have a problem. Okay, then which variance I've been talking about when I'm saying error? Okay, what kind of error I've been referring to? Okay, so let me just okay, contextualize it with the help of an example. So let me take with the same example, let's say. Okay, so suppose what I'm doing is I've been measuring the income of all the training program participants on the x-axis, and I'm measuring the consumption or the spending on the y-axis. Okay, so this is monthly income and this is monthly spending. Okay, so we have this consumption and the income spending. So suppose that there's a participant who earns on a monthly basis, okay, 50,000 rupees a month. Okay, then some participants earn 5,000 rupees a month. Some participants earn 60,000 rupees a month. Okay, 65,000, 70,000 rupees a month, 75,000 rupees. Okay, 80,000 rupees a month, 85,000, and so on. Okay, so that's how the monthly income goes. Okay, and then there are people, okay, whom okay, a participant, there's a participant X, okay, who's been actually been earning 50,000 rupees a month, but is spending 35,000. There's a participant okay, who's also earning 50,000 rupees a month, but who's spending, okay, 20,000. There's a participant who's earning 50,000 rupees a month, okay, is spending 48,000. Okay, so there are three participants who have been earning 50,000 rupees a month. Okay, then there are participants which have been earning 55,000 rupees a month. Okay, some of them are spending 35, some of them are spending, okay, 45, okay, and so on. Then there are participants who have been earning 60,000 rupees a month. Okay, so some are been spending 30,000 out of it, some are spending 50,000, some are spending 45,000. Okay, somewhere here. So each one of the category, there are number of participants, and that's what there is. Consumption pattern happens to be. Some are here, okay, then 70,000, some are here, okay, 75,000, some are spending here, okay, then for 80,000, there are people here, for 85,000, there's somebody here. So you are having this kind of a consumption versus the income relationship. Okay, now your idea is you need to know what is your, okay, consumption, okay, and the marginal propensity to consume times the income. So if you increase the income by 1 rupee or 100 rupee or 1,000 rupee, how much the consumption is going to increase? So I want to compute that, some alpha plus beta into consumption. That's a model which I want to fit in. Okay, now then this kind of a model, okay, so I fit a regression equation, and suppose my regression equation happens to be like this one, okay, which passes through in this entire spectrum here. Okay, now in this case, if that is the case, then what is your let me put it, okay, what is the error term? Now error term will be, if this is the line which you have fit in, this is your regression line. Okay, then where exactly is the error? Error term is the difference between, okay, your expected consumption based on the line, which is this one, okay, and your actual consumption. The difference between these two is your error term. Okay, so what is the error term here? This is the error term. Okay, then this is the error term 2. Okay, and then this is the error term 3. Okay, similarly here, this is one error term. This is the second error term. This is the third error term. Okay, for each one of the income level, there are different error term. Or let me call it as, this is 1, this is 2, this is 3, so this is 4, this is 5, this is 6, this is 7.
Sorry, sir.
Yes.
Sir, it is actual minus estimated, na? Y minus y bar, na?
So what is the y? Y is are these values, and what is y bar? Not y bar, but y cap.
Okay.
This is y cap. Regression line is telling you y cap. Okay. So you have these number. Okay, so this difference is, okay, it's your E8. In this case, it's E9. This will be E10. This will be E12, 11. This will be E12. Okay, so you have various okay, error term in this case. Okay, now what are the assumption is, okay, and probably what I'm just been computing in this case. Okay, so if I take all my error, okay, but only those error which is belonging to an income level of 50,000. Okay, so if my income level is 50,000, that's been fixed, that's given. And if given an income level of 50,000, what are my error numbers? Okay, this is E1, E2, and E3. So E1, E2, and E3, they belongs to when your income is 50. E4 is when, okay, income is 55,000. Okay, E8, E5, 6, 7, and 8 are when your income level is 60,000. So for each one of them, you have a, okay, different error term which has been given. So when your income level is 55,000, what are your error term? Which is E4. When your income level is 60,000, what are your error term? You have E5, E6, E7, E8. Okay, so you have all these values, these error terms. Now what you do of all these error terms, okay, you compute the variance. Okay, So you can compute, these are the 3 observations, you can compute a mean, add them together and divide it by 3. You can also compute a standard deviation here as well. You can also compute the variance as well. So you get a variance. Okay, so I'm interested here in the variance. So variance of the error term when income is 50,000. Then variance of the error term when income level is 55,000. Then variance of the error term, all these error term when income level is 60,000, and so on. For 70,000, 80,000, 75,000, 80,000, 85,000, you are having all these variances. Okay, so you have a variance here. 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 Okay, and let me call my first variance is variance sigma square 1. This is sigma square 2, sigma square 3, sigma square 4, sigma square 5, sigma square 6, okay, and sigma square 7. Okay, now what the assumption of homoscedasticity says? The assumption of homoscedasticity is that all these variances are the same. Okay, if that holds true, if all these variances are exactly equal to each other, they are all the same, then we have the assumption of homoscedasticity, okay, which has been upheld. Okay, so the assumption of homoscedasticity says that all these variances are exactly equal. If any one of them is not the same, okay, or some of them are not the same, okay, or they all are different from each other, none of them are exactly the same, okay, all those situations are referred as the situation of heterozygosity. Okay, so as the word says, homo means same, okay, sedasticity means variation, okay, so homoscedasticity means same variance. Okay, so if the variances remains the same, that's a homoscedasticity. If the variance is not the same, any one is different, or any two is different, or all of them are different, they all are referred as by the notion called heterozygosity. Okay, that's the idea of the assumption of homoscedasticity and heterozygosity. Okay, when you have homoscedasticity, your data shows homoscedasticity. Okay, then go ahead, interpret the result. Okay, whatever regression you have run, interpret the result. Okay, and there's no problem in that case. But if the assumption is getting violated, you have heterozygosity. Okay, so here the variance is smaller. Here the variance is larger. Okay, here the variance is smaller. Here the variance is okay, some medium level. Here the variance is again smaller. So if it is not the same, okay, it has been differing from each other, okay, which in most financial time series, okay, it generally happens. Okay, these variances are not the same. Okay, if these variances are the same, okay, then you have a homoscedasticity being uphold. Okay, and when your variances are not the same, you have the assumption of heterozygosity. The violation of the assumption of homoscedasticity, that situation is referred as heterozygosity. Okay, now another thing, which is the next violation, is that if the error term here E4, okay, and the error term in the previous case, okay, in general, okay, over a period of time, okay, if this error term in this time span and this error term in this time span, okay, suppose these are measured over time, not as income level, okay, this is my consumption and my income, okay, and every year I get a 5,000 rupees of as an increment. Suppose that's the case. Okay, so I have a error term here, I have an error term here. So when it was the year 2000, I was earning 50,000 rupees a month. Then it was 2001, then it was 2002, then it was 2003, 2004. Okay, so over this time period, I was spending some amount of consumption, and I have my error terms computed here. Okay, so error term for 2000, error term for 2001, error term for 2002, error term for 2003, error term for 2004. Okay, this is what the sequence was like. If my error term for this year is dependent upon the okay, if there's any correlation between these, okay, that means today's error term is dependent upon yesterday's error term, okay, or it shares a relationship with the yesterday's error term. If there is this okay relationship which has been there, then you have a problem of autocorrelation. Okay, problem of autocorrelation is mostly okay, a time series phenomena. Okay, it generally do not okay appear in the cross-sectional setting. Okay, it's generally a time series phenomena. Okay, but it doesn't mean that there is it will not be there in a cross-sectional setting. Okay, you can have certain instances, for example, a snowball sampling based data collection, where you might have this kind of an okay autocorrelation problem as well. Okay? But generally this is not found in a cross-sectional data set. Okay? So in a time series data set, when you have this kind of autocorrelation, this kind of error term computed, and these error terms share some sort of a relationship between the previous error term, then you have a problem of autocorrelation. Okay, so there is a problem of heterozygosity, where the variances of the error term does not have, they are not the same. Okay, they not have the same constant variation, and if the error term for this time span is related to the previous error term, then okay, you have a of autocorrelation. And if you have both the problems, okay, which is generally found in a financial time series, okay, which okay is again okay more problematic in that case. Okay, however, there are ways to handle for that. Okay, so there's a problem of heterozygosity, there's a problem of autocorrelation. Why I've been actually talking about both these okay problems simultaneously, because their consequences are quite similar, and their okay remedies are also quite connected as well. Okay, hence I've been taking them okay together. Okay, any question? Okay, so what is the difference between autocorrelation and serial correlation? They are one and the same thing. Okay, we use the as interchangeably. Okay, quite often we use it interchangeably only. Autocorrelation, okay, as the word says, it's the auto. Auto means with self. Okay, so you are computing a correlation with itself. Okay, that's what the error term was signifying. While in the case of serial correlation, you prepare it in a series. Okay, and that series generally happens. So with a time series, okay, so you can also compute there as well. Okay, so okay, for all practical purposes, autocorrelation and serial correlation is one and the same thing. Okay, there's no difference between these two. Okay. Okay, so any other question on that? Okay, so how would you compute the sigma? Okay, how you compute the standard deviation? Okay, it's the same way. You are having, let's say, suppose that there are 3 observations here. Okay, I think I moved it away. Okay, so when your income level was 50,000, you have 3 error term, E1, E2, E3. How you compute the variance of the error term? Okay, so you take that, you take these 3 values, you compute their mean. Okay, from each of these observations, you deduct the mean. Okay, you square them. This is E1, E2, E bar.
Dr. Naren, sorry to interrupt you, sir. If you could see the chat, I think there are some questions. The last one was asked by Sunita.
That's what I was responding to.
Yes,
okay.
sure.
So somebody
sure,
asked, yeah, somebody asked what is how you compute the variance of the error term. Okay, so
Yes.
E minus E bar square, then E2 minus E bar square, then E3 minus E bar square. Okay, sum them, divided by okay 3 minus 1, and that will be your variance in that case. Okay, so how you compute a variance? Okay, so I'm just describing how to compute a variance. How you compute a variance if you have these 3 observations? You simply compute that accordingly. So that's what this okay the variance computation will be. Okay, so which test can be applied if data does not belongs to a time series? Okay, for testing what? Okay, I don't know which test you have been talking about. Which test can be applied if data does not belong to time series data set? So if you don't have a time series data set, okay, then and still want to go for heterozygosity testing, I'll come to that. Okay, itself. When you have a time series data set, okay, and then you want to test for heterozygosity, okay, then there are other tests as well, okay. I will come to it one by one. Okay. Okay, so let's move forward. Okay. Okay, so what this actually means that my variance of the error term for a given independent variable or given predicted variable, you compute that, and that's a constant number. Okay, there's no subscript t here or subscript I here because it is for I. Okay, so there's no subscript. Everyone is having the same variance. Let us suppose it's a sigma square. Okay, so if all our error term has the same variance, okay, that's what we will be having as the assumption of homosedasticity. Okay, so when you look at residuals along income level or your independent variable x or your predicted y cap, okay, if you have these observations, so for any given level of income, let's say 20, okay, if you compute a variance here, okay, that variance and the variance which has been here at 60 level, variance at here at 100 level, okay, for all levels, okay, I'm just putting bars, okay, arbitrarily. If you take these variances, okay, at each of these levels, you compute a variance of observation here, which again follows certain distribution, okay. So this distribution is generally, again, second assumption violation which I was talking about, that each of these distribution is normally distributed. Okay, that was one of my assumption. And second, because it's normally distributed, it has a mean. And what is the mean of the residual? That was my assumption number one. Assumption number one was saying mean of these error terms was supposed to be 0. So you have a 0 mean. Okay. Then you have variance 1, 2, 3, okay, 4, 1, 2, 3, 4, 5. Okay. There will be more, obviously. Okay. So assumption number one was saying that all these means are supposed to be 0. The assumption number 2 was saying that all these distributions were supposed to be normal distributed. The third assumption I'm talking about, that the variance of all these error terms for a given independent variable, okay, they are supposed to be equal. Okay, and if they are, okay, then how does the graph look like? This is a typical graph of homosedasticity. Okay, where you look, if you look at the range, okay, variance is also a measure of dispersion. Range, which is max minus minimum, is also a measure of dispersion. So you can pictorially or crudely you can get the similar idea, okay, by looking at a range or looking at the variance itself. So in this case, okay, if you look at the distribution of the error term for a given income level or given independent variable, they are being distributed quite similarly. Okay, it's a quite range bound observation. All these okay, error terms are being there in a particular band only. Okay, if that's not, okay, for example, this one, okay, you continue to have increasing variance. Variance has actually been increasing. Here the variance is less. Here the variance is less. Here again the variance has become more. Here even a much more larger variance. Here again the variance has actually been enhancing. This is the typical case of heterozygosity as well. There are many other versions of heterozygosity. For example, in this case, again the residual has been measured on the y-axis. X-axis either is an independent variable, or if you have more than one independent variable, you can also take as y cap, the predicted y values. So in this case, what has happened is, okay, this is expanding. Okay, what is expanding is the spread of the error term. In this case, okay, the variance is not much. Okay, dispersion is very low, but this dispersion is expanding. Okay, you have a larger and larger dispersion in this case. Okay, so again, that's not homozydastic. It's not the same variance throughout. So this is again an example of heterozygosity. Okay, when you can also have something like this one here. What is on the y-axis might be your dependent variable y itself, and here it could be independent variable. But again, the issue remains the same. Something like consumption versus income. Okay, that it is continuously expanding. Okay, and this is typically the case when I've been earning 100,000 rupees, okay, 1 lakh rupees a month, okay, somebody might be spending only 60,000, somebody might be spending, okay, consuming, they are earning 1 lakh rupee a month, they are, okay, consuming 1 lakh rupee of the month. That could also happen, okay. But somebody who's been earning 10,000 rupees a month, okay, or 5,000 rupees a month, might be consuming almost the entire amount itself, but will not have that much amount of variance, okay. So even if you look at more realistically as well, okay, what about those people who are in the lower income strata? They have been earning 10,000 or 15,000 or 20,000 rupees a month, okay. Most of their consumption will be there in the food articles and clothing itself, okay. Almost out of the 20,000, probably 15, okay, to 17 or even 19 or entire 20,000 will be consumed only for this kind of activity. They will not have a larger variation. Almost the entire sum will be consumed by them, okay. Their income has been lower, and so does, and given a certain level of the living standard of living, okay, the entire thing might have been consumed there itself. When people have been earning more and more, they have been earning 40,000, so they can still spend 20,000, okay, on rent or food and clothing, but now they have some discretionary income which they can spend or they may not spend. They can save the entire thing together, or what they could do is, okay, they can go for a holiday, okay, somewhere they can go. If they can't go to Shimla, they can go to, okay, Dubai, or they can go to New York. Okay, they can use it provided when they have so much amount of income in that case. So people who are in the higher income strata, okay, they will have a much larger variation. Some might be consuming less, some might be consuming the entire thing as well. So there will be larger variation. But somebody who's been earning only 10,000 rupees a month or 20,000 rupees a month, okay, will be spending almost the entire sum only on the two items, which might be food, clothing, okay, rent and other. Okay, so this is also quite natural that this keeps on okay, expanding, okay, when you look at the consumption versus income relationship. Again, here the residuals have been there, and here it's the independent variable. Again, it's been expanding, okay. Not every time expanding, okay. If it is also going down as well, that could also happen. So here there is a, okay, much variation here, and this could also be here. So earlier there was a larger variation, then it narrows down, and then again it starts expanding as well. This is also heterozygosity. Anything other than a constant variation is a situation of heterozygosity, and it can come from, okay, different reasons itself. Okay, then why should you worry about heterozygosity at all? What are the consequences? The consequences that, okay, you are okay. Remember, I talked about the properties of a estimate. Okay? So you are still having a linear estimate. So normality is not what has been affected. You still have an unbiased estimate. You still have a consistent estimate, but the only problem in that case is the estimates will not be efficient. Okay, so they will not be called as a blue estimate. Okay, and remember what I talked about as efficiency. Okay, efficiency says that your measure of standard error, okay, will be wrong. If the measure of standard error will be wrong, then if you construct a confidence interval, okay, so remember 4.4, okay, to 4.2 to 4.6, okay, this was my estimates of a variable cost. So variable cost could be anywhere between 4.2, okay, per unit, or 4.6 per unit, but the mean value was 4.4. Now, then your lower limit and upper limit of the confidence interval, they will all be wrong, because that is dependent upon something called as standard error. So when you have heterozygosity, okay, what is affected is a standard error. And if standard error is wrong, your confidence interval construction is also wrong. And if you want to conduct any hypothesis testing, for example, T, okay, which is your computed alpha value minus 0 divided by standard error. So again, if the standard error is wrong, your T statistics also wrong. Okay, so whenever you have the heterozygosity problem, and also whenever you have autocorrelation problem, as I was saying that the two are okay, quite similar in terms of consequences and the remedies as well. So even when you have the problem of autocorrelation, or whenever you have a problem of heterozygosity, okay, your estimates of alpha, beta, they are not efficient, which in other words means the standard error which you computed in your output is also wrong. If that's also wrong, that means your confidence interval is also being wrong, or your hypothesis testing will also be wrong. So you cannot use it for all this purpose. So what will be right? The right will be, okay, your point estimate which you have arrived at alpha and beta, which was 1693 and 4.4. Okay, they are fine. Okay, you need not worry about heterozygosity. Okay, problem when you are only being concerned about that. What is my estimate of fixed cost? That's all. Not a lower limit or upper limit of that. And what is my estimate of my variable cost, which is 4.4 per unit. Okay, I'm also not bothered about what is the lower level of the lowest level of variable cost, what could be the highest level of my variable cost. If you're not bothered about that, you are not bothered about heterozygosity problem. You are also not bothered about autocorrelation problem. Okay, but when you need to go for a hypothesis testing or confidence interval construction, you need to be worrying about the problem of heterozygosity as well as autocorrelation. When you have heterozygosity, your standard error of, okay, your beta, okay, this is what will be giving rise to your standard error. So standard error, the variance of the beta, okay, which is in the case of homoscedasticity is this number, okay, but in the presence of heterozygosity, it will be entirely a different number. This function is different from this one. And you say whenever you run a regression, you arrive with this one, okay, and you do not consider this one. So there is a change in your standard error estimate. True estimate is this one. This is true estimate, and this is what you actually computed from your OLS model. Okay, and now these two are quite different from each other. Okay, so as a result, your standard error estimated will be wrong. Okay. So as a consequence, what will be there? Your estimates of standard error in your output will be wrong, will be incorrect, will be biased and unreliable. As a result, if you conduct any of the hypothesis testing or you construct the confidence interval, they will also be problematic. Okay. However, your estimates are still linear, still unbiased, but they are not blue estimate because the best efficiency, okay, that the best aspect of your attribute, which is the efficiency aspect, okay, will be compromised in such a situation. Okay, so they are no longer estimates. Your standard error estimates are wrong. Your estimates are no longer efficient itself. Okay. There are multiple examples which even the textbooks talks about. Okay, I talked about that income versus consumption example itself. Okay, there are two more examples, standard example, which is also been given. Okay, something called as number of typos, okay, which you make, and your experience, typing experience. Okay, in terms of number of hours. Okay, so when you are inexperienced, you make so many mistakes. Okay, so if I take 100 people and they are having just 2 hours of experience, okay, they didn't type in their entire life, and they type just for 2 hours, and after 2 hours you take their test and you compute what are the number of typing mistakes, number of typos they have made. So out of these 100 people, okay, some may make a higher mistake, some may make lower mistakes. Okay, so they will be having, okay, larger, not just a larger mistake, but larger spectrum of the mistake as well. When you have 500 hours of typing, okay, so you still be making a typing mistake. It doesn't mean that experienced typists, okay, don't make any mistake, but they will all those 100 people who have been having 500 hours of typing experience, okay, they will be making a mistake, but their range of making a mistake will be much narrower. So as the experience goes up, okay, people starts making not just a lesser and lesser mistakes. Okay, it's a downward sloping curve, but the variation in the typing mistakes, okay, that also gets lower and lower as well. That's called as a learning curve effect. Okay, so when you learn more, okay, obviously when you become more proficient, okay, the range in which you are also making a typing mistakes will also be come down as well. So you will be having a decreasing, okay, variation as well. That's also a heterozygosity. Okay, which is quite usual. Okay, this is nothing unusual about it. It's quite usual, but then this is also, okay, against my assumption. My assumption was saying same okay, amount of variation throughout. Okay, another example which has been given is, okay, the speed versus the extent of fatality. Okay, so we observe the various accident which has happened in a particular locality. Okay, and we observe what is the extent of fatality which has happened. Okay, so it was just a small bruise, or okay, probably there was a larger fracture, okay, or okay, much severe, okay, a near death kind of a, okay, a situation. Okay, so we have extent of fatality on the y-axis and the speed immediately before the, okay, in kilometer per hour when the accident happened. Okay, so when the speed is very low, okay, there are chances that you still meet an accident. Not every time it's your fault of meeting with the accident itself. Okay, but the extent of fatality will be lesser. Okay, you will have some small bruises, okay, or something like that. But when you are, okay, going at a speed of 240 kilometer per hour, okay, anything can happen. Okay, and not just the, okay, you can also escape from 140 kilometer per hour speed as well, okay, with a small scratches only, but you can also quite okay, having, okay, injuries which are fatal in nature as well. Okay, so as the speed goes up, okay, it's not just the fatality, the extent of fatality goes up, it's also the variation in fatality also goes up as well. Okay, so you might also escape, okay, when you are at okay, 150 kilometer per hour or 70 kilometer per hour. Okay, but this variation of extent of fatality can actually keeps on increasing when you are, okay, driving your car or your vehicle at a much higher speed. Okay, so this is again a situation of heterozygosity as well. Okay, anything other than a constant one, okay, this is supposed to be, okay, constantly moving downward. This should be constantly, okay, upward itself, but all in the range bound. If that happens, that's a situation of homosedasticity. Otherwise you will have a situation of heterozygosity. Okay, so it can arise for many of these issues as well. So when you are looking for urban and rural, okay, income and consumption relationship, you might again have a heterozygosity. Okay, when you, the way you derive your sample strategy, that could also be there. Okay, when you started collecting your data, you were not sure about, okay, how to correctly estimate it, but over a period of time, okay, your method of improvement, data collection improves, and as a result, you again can have, okay, variation in your data. We give rise to heterozygosity, skewness. So there are multiple reasons of the presence of heterozygosity. Okay. Okay. Now the question is how to detect it. Okay. And the one way of detection I've already talked about. Okay. What you do is, okay, simply plot the residuals. Okay. You can have a graphical method for detection of heterozygosity. So what you do is, okay, there are two options within the graphical method as well. What you do is you take the residuals, okay, on the y-axis, and on the x-axis, okay, you have your x variable x, which is your independent variable. And if you have more than one independent variable, okay, then you also have a choice. You can also take the predicted value of y. Don't take y. Okay, you take predicted value of y. So you have residuals here, okay, on the y-axis, and you put the predicted value of your dependent variable on the x-axis, and you plot the graph. Or alternatively, what you could do is, okay, as I was showing in my first example, you take your dependent variable, for example, consumption, okay, consumption on the, okay, y-axis, and you take your independent variable income on the x-axis. Okay, you can do that as well. Okay, or if you have more than one independent variable, you can take the predicted value of the consumption as well. Okay, on the x-axis, and then you simply look at the graph. Okay, if it goes range bound, okay, you have a homoscedasticity. If here again you see some sort of a range bound movement, you again have a situation of homoscedasticity. Otherwise, there will be a situation of heterozygosity. Okay, so if you see something like this one, where the residuals are on the y-axis and you have independent variable on the x-axis, just Just a second.
हेलो सर, आपकी वॉइस नहीं आ रही है। हेलो
Naren sir, you are muted. Please unmute yourself, sir. Dear participant, please wait. Might be is busy on another call.
Okay,
Yeah.
so
Yeah.
So what I've been talking about is, okay, in a graphical way, okay, when you have been measuring the residuals on the x-axis, when you have been measuring residuals on the y-axis and you are measuring the income or other on, okay, here it was your independent variable on the x-axis, and when you see, okay, what is the point zero level, okay, this was my point zero. So there was variation which is here, okay, but this variation has now started, okay, changing abruptly. Okay, so this is again a situation where you have the situation of heterozygosity. Okay, 1 second.
Dr. Naren, I think you're mistakenly muted. Kindly unmute yourself, sir.
Hello, am I audible?
Yeah, right now you are.
Okay.
So.
Okay, so what I was referring to from a graphical method was that you can get some pictorial understanding regarding the heterozygosity. For example, let me take one more example here again. You are having residuals on the y-axis, and you are having a time. Okay, there's no independent variable, so you're measuring time on the x-axis. So if you again see the sales, there was a sales data, and it has actually been expanding. The variation in sales has actually been expanding in that case. That's again the situation of heterozygosity. Whenever you see any pattern other than a horizontal one, okay, that's an indicator of a presence of heterozygosity. Not every time, okay, you need to go for a formal statistical test for that. You can also do it anytime, okay, that's not always a non-mandatory thing, okay, but whenever you can also gauge the situation of heterozygosity accordingly. So here the variance in the sales has actually been expanding, okay, and when I'm saying variance, I'm just looking at from max minus minimum. So at any given level, okay, of the point in time here, what is the max minus minimum, okay, that is also a reasonable way of assessing how much amount of variance you can have there, okay. So if you have something like this one, the situation of heterozygosity, okay, could also be judged from this perspective as well, okay. Another way in which you can graphically, you can also detect it, okay, where what you do is you don't put residual here, you put square of the residual, okay. So it is residual square, okay. So you put square of the residual on the y-axis, and on the x-axis either you put your independent variable or you put your predicted y value, okay, not the actual y value but predicted y values. You put predicted y values here and the residual square on the y-axis, and then you see in terms of the graph as well, okay. So if you see again a constant, okay, change in the square, residual square against the y hat, okay, that's a situation of homosedasticity or no heterozygosity. Otherwise, if you see any pattern other than this, okay, including increasing one, if you see something like this one, okay, that's a heterozygosity. If you see this one as well, that's also heterozygosity. It has to be only horizontal against a residual square versus, okay, the y hat, okay, domain, okay, plane, okay. So if you see something like this one, this is also heterozygosity. This is also heterozygosity. If it increases and then decreases, that's also heterozygosity. It decreases, then flat, then increases, that's also heterozygosity. Or it increases at an increasing scale, exponentially been increasing, that's also heterozygosity. Anything other than a horizontal, okay, change here is a situation of heterozygosity, okay. So if you want to have a look at, okay, from a data perspective, okay, let's use one data and see the heterozygosity issue, okay. So there is a data, okay, a file which I have shared with you, which has four variable. The variable number one is distance traveled, how much amount of okay, how far a family, okay, this is belongs to various family members, okay, observations which are being collected from various families. So one family who has okay, in the next summer vacation, they have made a trip to somewhere which is 902 kilometers away from their home. Second family has traveled to 491 kilometers. Third family has traveled to 1,841 kilometers. So this is the distance traveled by the family. This is the per month income, okay, of family, okay, in thousands of rupees. This is the average age of family members in that family, and this is the number of kids in that family. Okay, so we have this kind of a data, and we want to run a regression. We want to assess how far, okay, people generally go on vacation, how distant far they actually travel, okay. Is that a function of income level, age, okay, or number of kids. Okay, is there any relationship between that itself? So let me take this data, okay, put it into the stata and see, okay, do we get any sort of a heterozygosity itself? Okay, so let me just use that. I clear this. Okay, so I go for file, import, Excel, okay, and I import something called as distance traveled. Okay, so in the distance traveled, okay, I have age, distance, income, and number of kids. Okay, the first row is your observations itself, so that becomes the header of the column. Okay, and I press OK. Okay. It says it has imported, but let me have a view. So let me just pick up that. Okay, so I have number of observations, okay, which has been collected. So there are how many number of families who have been, okay, whose data has been collected. That's a 200 families, okay, whose data has actually been collected. And you have age, distance, income, and number of kids in the family. Okay, so I want to run a regression of distance with age, income, and number of kids. Okay, so let me just use that. I go to statistics, linear model, okay, linear regression. So let me pick up my independent variable. My dependent variable is distance traveled. My independent variable is age, income, and number of kids. Okay. These are my independent variable. This one is my dependent variable, and I want to, okay, run a regression. Okay, so this is a regression which I have run it. Okay, I got a coefficient. Okay, and as I said, okay, once you have an output, it doesn't mean that you need to rush for okay, interpreting that. Okay, start interpreting that this is significant, this is insignificant. Okay, start doing that. Okay, don't rush for it. Just hold on. Okay, look for whether those assumptions which are there at the back of running this regression, they have been valid or not. Okay, so if we simply store my residual and okay, just see it, okay, how it's actually been changing. Okay, that's what I could do. Okay, while looking for okay, a pictorial description of my variation in the residual itself. Okay, so what I do is now I go to let me remove this. So I go to statistics. I go to post estimation. Okay, I go to prediction. Okay, and I store my residual because I don't have residual as of now. So let me store my residual. So let me put resid, okay, as my variable, and let me store it with the name resid. Okay, so let me press OK. That has stored a variable resid in my file. Okay, I can see that as well. I click on this, and there are resid which have been stored here. Okay, so I want to have a look of resid with each of these independent variable. Okay, or I can have a square of resid and okay, I'll just have it with the independent variable, or okay, a predicted value itself. I can do it for any of the stage. Okay, but let me just show you peculiar here, okay, because it's an art. Okay, you need to you need to try all possible combination in a particular situation. Okay, so here I know, okay, probably with the income level there is a larger variation which has been possible. Okay, but you can try with all possible combination as well. So let me have this graph, a two-way graph, scatter plot. Okay, wherein I'm just creating a scatter where my y variable is resid and my x variable is okay. Let me take age first. The deposit comes up. Okay, I have not cleared it. We graph. Let me clear all. let me create one. So I want to have scattered where I have residual on the y-axis and I have age on the x-axis. Let me have the graph. Okay, this is against the age. You have residual here and you have the age here. Okay, you see any discernible pattern here. Okay, if you see, okay, that if they have been changing, okay, in a range bound fashion or not. Okay, pictorially with the age, okay, somebody might say, okay, it seems to be expanding as well. Okay, but then it converges to something. Okay, so pictorial view cannot always give you the okay correct description. Okay, but yes, okay, that could be put up as a first okay hand exercise itself. So let me take okay, one more. Go to graph, scatter plot. Okay, let me edit it. So I don't take it on with age, I take it with the income. Okay, now see with the income level itself. Okay, as the income is increasing, okay, what is happening to the variance of the residual? Okay, the variance of residual is expanding with the income. Okay, this is clearly a case of heterozygosity in your data set. Okay, so one way in which you can detect heterozygosity is using the notion of using the graphical view. Okay, another, okay, if you are not always so sure about that, okay, so what you could do, is there any formal test for okay, getting your heterozygosity as well? Okay, the answer is yes. Okay, you can also have a formal test of heterozygosity as well. Again, okay, you can need to go to post estimation. Post estimation. Okay, you have specification, diagnostic, and goodness of fit. There are tests of heterozygosity. Okay, there are many other tests as well. Okay, so I go for tests of heterozygosity. Okay, so you have het test, okay, which can also be used, and you have Bruce-Pagan test to compute. Okay, so you have choice here, okay, to opt for. Where let us use the Bruce-Pagan test for heterozygosity. Okay, I press OK, and you have okay, tests of heterozygosity here. Okay, the result is actually being generated here. So in this case, sorry, you have okay, formal test of heterozygosity. Okay, where one such popular test is a Bruce-Pagan test. Where what is the null hypothesis? The null hypothesis H0 is that you have a constant variance. Okay, that means that's an assumption of homosedasticity. Okay, if you okay, if you have the US English, so it will say not SCED, okay, but SKED. Okay, like schedule versus schedule. Okay, in the US English, you pronounce it as a schedule. Okay, in the British okay, accent, you are pronouncing as a schedule. Okay, so heteroskedasticity is pronounced in the US version. Okay, while in British one, okay, you have SCD. Okay, SCED. Okay, dasticity. Okay, that's a difference. So but they are basically the same thing. Okay, schedule and schedule is the one in the same thing. Okay, only the accent difference has been there. Okay, so this is saying constant variance. Okay, so homoskedasticity is my null hypothesis. What is the p-value? The p-value is 0.0034, which is less than 0.05. That means you reject your null. Okay, and what is the null? Null was saying that you have homoscedasticity, that is getting rejected. So that means you have heteroscedasticity in your data set. So the test is also formally proving that as well. Okay, so whether you have looked up at the graph and you have also looked up for the test, okay, they are indicating the same thing, that you have a problem of sorry, heteroscedasticity in your data set. Okay. Okay, so let me take. Okay, so is Okay, somebody asked, these tests are available in SPSS? Yes, most of these tests are available in SPSS. Okay, otherwise there are plugins which have been available for you to conduct that. And somebody is asking that if the assumption of exogeneity is being satisfied, okay, then is it sufficient condition that we need to go for? We need to go for other tests. Okay. Yes, okay. The exogeneity is you can't test exogeneity in a cross-sectional or time series data. Okay, the test for exogeneity can only be done in a panel setting. Okay, so you don't have something available for exogeneity unless you have a theory backing that itself. So if theoretically you are saying there is a exogeneity, that's another aspect. But yes, if the issue which is been there, for example, this learning curve model, so you will bound to have heterozygosity, whether there is a strict exogeneity which has been prevailing, but when you have a learning curve effect, that will still have the issue with respect to the presence of heterozygosity. So having exogeneity may not always be giving. If your exogeneity is giving rise to heterozygosity, only then you can take refuge under the exogeneity issue, not otherwise. Another has asked for if you have many categorical variable as independent variable, then how to deal with it? Is there any possibility of done? When you have more categorical variable in your data set, that's not an issue at all. You can still run a regression. Regression is a much versatile a tool. When you have only independent variable, suppose you have the y variable. Sorry. So suppose you have okay. So when you only have y as a dependent variable, and you all your independent variable are categorical only, d1, d2, d3. That's a situation of ANOVA. So whether you conduct ANOVA or you conduct it using a regression model, you get the same answer. If any one of the independent variables, some are x1, some are your categorical variable d1, d2, d3, you can simply run a regression. That's again not an issue at all. So that can still be done. You will not have so possibility of a dummy trap will be there. If you as many categories you are having, as many dummy if you put, you will still have a problem of a dummy variable trap as well. If your dependent variable is a categorical one, d1, d2, so then that's a different class of model, but that's also a regression model. So you might opt for logic model, probit model, tobit model, that's what you could also do it. So if you are looking for dealing with the dummy variable trap, so always have the number of dummy variable less, as one less than the number of categories. So if, suppose you are having male and female, there are two categories, so only introduce one dummy. If you have three categories, male, female, and neutral, other, then you introduce two dummy variables. So always introduce one less a dummy variable to get out of the dummy variable trap. Heterozygosity is a phenomena which as I've been discussing may not necessarily be affected by the presence or absence of the categorical variable as well. Then what should be applied after the heterozygosity is found in the data set? So let me come to that. What to do in such a situation? So when you have heterozygosity present in the data, we have already seen that you have heterozygosity present in the data. So there are two choices which you have, and that's what I will also come to it. So there you have two choices, and the choice is I think I'll put it. Just a second. Okay, so I think it was a different slide altogether. Okay. Anyway, you have two choices in the presence of heterozygosity. Now you have already seen that there is a heterozygosity in your data. So let me put it this way. Okay, so there are two choices. If you have heterozygosity in your data set, okay, if you have heterozygosity in your data set, or you have autocorrelation, okay, present in your data set, any of the two situations, if you have that, okay, you have two choices. One choice is you expressly model it. Okay. Another way is that you go for a large sample based correction. These are the two choices which you have. For example, in my the example which I just picked up, distance traveled versus income. Okay. Now you are saying that as the income goes up, the variance of the residual term is actually been expanding. Okay, if this has been happening, so what you do it, you have already seen that the variance of the error term is a function of the income. So you already know this information beforehand, okay, and for that you need to make an effort as well. People generally don't do it, okay, but if you do it in that case, you have to expressly model it, and then you can use something called as a GLS, generalized least square. We have been using ordinary least square. You make one modification in that, you use weighted least square, or we call them a generalized least square. Okay, so in that case what you could do is you expressly model it. So you say variance of my error term is a variance, a constant number, multiplied by my income, the variable. So higher the income, higher is the variance of the error term. So if the income rises, variance also rises. If income is lower, variance is also been lower. So when you run a regression, y is equal to alpha plus beta x, you use this express modeling, and you use a GLS in that case. That's what you could do it, for expressly modeling my this extra piece of information that the variance of the residual term is affected by the income. That's one way. Or another way is where you can make certain correction factor, and people are so much using this, they have now actually stopped bothering about heterozygosity and autocorrelation. This correction factor is been used quite extensively, quite rather obsessively. It has been used. So there's something called as heterozygosity consistent estimates. So you can generate that, and that was given by Newey and West. So they use this kind of a correction mechanism. So there are various versions. Heterozygosity consistent estimate, they call them HC0, HC1. There are 6-7 versions of that. And there's also called HAC consistent estimate, which is for both heterozygosity as well as autocorrelation. So when you have both autocorrelation problem as well as the heterozygosity problem, then you can opt for HAC estimate, which is large sample corrected estimates. And if you only have heterozygosity problem, not of autocorrelation, then you can opt for heterozygosity consistent estimate, HC0, HC1, and so on. These are the two major techniques available for getting this corrected as well. So how you are actually been opting for that? You can do it in your regression model. I go to linear regression. So I have the same dependent and the independent variable. So what I will be using is I can use a weighting series. I think weighting type is none. Sampling weight. What is the idea here? So if I can use a weighted least square, which is expressly modeling for that. So if I use that, let me just check out. Yeah. So you can make modification based on your weighting mechanism itself. So that's one way. okay, wherein you have earlier you do not have this mechanism, weighting mechanism. I think that was 2 up. Okay, so here you already have a weighting mechanism. You have used the income as a weight, and why you have used income as a weight is, okay, because you are finding that the error term square was proportional to your income. It was not proportional to age. It is not proportional to number of kids. It was proportional to income. But how I come to know? Okay, you need to do an extra effort, extra piece. Okay, a piece of mile you need to cover for digging out this information. You need to have a time, okay, effort, and the patience for doing that itself. Okay, I did it. Okay, I generated a residual, then I tested whether it relates to income, whether it relates to the age. I've shown you both the graphs. Okay, I could have done it for the third one as well, number of kids as well. Okay, but you need to do this stuff before you actually opt for first methodology of making a correction. So you take weighting mechanism, you take the income as a weight, okay, and then you run a regression. Okay, as a result of running this regression, now the standard error which has been obtained are robust one. Okay, and now the p-value is you can make a comment accordingly. Okay, only when you get this kind of a robust standard error, you opt for, okay, this kind of a correction mechanism. Okay, so one way in which you can correct for heterozygosity is opting for GLS procedure, where you use weighting okay, series, use a weighted series for computing what is the correct standard error, rectified standard error. Okay. Secondly, what you could alternatively opt for is, okay, which I was showing you the second option. Okay, you compute your robust standard error, so you go for same linear regression, and in the weighting, okay, so you don't choose anything, but you now opt for something called as SC/robust. Okay, so here you use a robust standard error procedure. Okay, and as I was telling you in the previous case, you can also opt for bootstrapping, jackknifing, so that option has also been available here as well. So I opt for default I opt for a robust standard error. Okay, so which is a bias corrected itself. Okay, so as I was saying that there are different versions of this. Okay, so you have by default, which is correction for the degrees of freedom. Okay, there are more options. Okay, best for heterozygosity, best for homosedasticity, and that's for default. So when you have heterozygosity, which you have already seen here, okay, so what you could do is you can opt for heterozygostic data set. So I can opt for 1/1 minus h raised to power 2. That's a correction which I can opt for, and either you opt for default, okay, or you can opt for the heterozygosity itself. Okay, so I click OK, and again you get your robust standard error. This is HC3. It's a third version which has been there. Okay, if you are not sure about which version I need to go for, okay, those data is telling you that as well. But if you are not clear about that as well, you can opt for the statistics, linear model, and SC robust. You can opt for the default one as well. Okay, you can do that. People have actually been using it so often that they simply put, okay, what they do is you run a model, okay, then you test for whether there's a heterozygosity, okay, then they use this robust standard error. Okay, nowadays, okay, people have so much used that itself. Okay, so when they use a model, they don't simply test for whether there's a heterozygosity or not. They simply say what are my robust standard error. They don't even compute what is the simple OLS model. Okay, test for heterozygosity and then go for robust. They simply don't test for OLS. Okay, they always go for robust standard error itself. Okay, and that's way they can actually handle heterozygosity, okay, directly itself. But provided there's one catch here. Okay, your robust standard error functions, okay, works for a large sample. Okay, here the number of observation is 200. If you think that's large enough, okay, you can apply a robust standard error correction mechanism here itself. Okay, what is getting corrected in this case, or probably how things are getting corrected in this robust standard error. Okay, that's there in the Excel file, which I've also shared with you all. Okay, so if you have been interested, you can also, though it's a self-explanatory white correction procedure, okay, distance exercise, it's already been there, and you can see the detailed working, but it's a more involving in such a situation. Okay, so that's the one way, making a correction, and that was. So that was based on weighting scheme. You use a income as a weighting scheme, and you make correction based on that. Okay, or you can also opt for the correction procedure based on the. I think that was there above only. The site-based heterozygosity consistent estimate. So you can also get that as well. So you have both these. Just to evaluate which one is better, which one is okay.
So sorry to interrupt you, sir. If you take the robust standard error, then it will automatically adjust the heterozygosity, Suna.
Yes. Okay. It's a procedure to adjust for heterozygosity. Okay. So robust means
for
that you are
cross-sectional data.
Okay, on a cross-sectional data. Yes. When you have time series data, probably you should check for autocorrelation as well. Almost in 90% cases, you will be having heterozygosity problem as well as autocorrelation problem.
In finance data, we find a lot of times this heterozygosity issue.
Yeah.
And
so then
if the model is significant, then if you take the robust standard error, we find there is an improvement in models. Lot of model is handled.
So probably it's coupled in most of the financial data set. It's heterozygosity problem along with the autocorrelation problem itself. So then you opt for HAC robust. Don't opt for simple robust. You opt for HAC, heterozygosity and autocorrelation consistent estimate.
Sir, can you show it in
stata,
sir?
Yes,
how it will be HAC?
In eViews, I'm sure about. Stata, I need to search for it. But in this data,
sir, what is the name? Please repeat, sir. HAC.
It's heterozygosity, autocorrelation, consistent estimates of standard error. And
okay, sir.
But in Stata, you need to have a time series data. Only then autocorrelation tab will become activated. As of now, I have not defined my data as time series data. So I need to define my data, import my data, define it as a time series data, and then go for testing for autocorrelation and other. At least in the previous version, I really need to see for that as well. Okay, so there are some more questions on this. Okay, how to calculate residuals. In the post estimation, again, you can store those residual. In predict. In post estimation, you have a predict section where you can use it to store the residual. Can we use bias correction factor? These HC, the heterozygosity consistent versions. They are HC0, 1, 2, 3, 4, 5, 6. There are 6, 7 versions of that. Each author has tried to improve the previous methodology. So these are nothing but these are bias corrections. Only which has been done. Just for the correcting the biases coming from the heterozygosity. If the data contains negative values, then can we run a regression? Yes, you can run a regression. Having a negative or positive value is not an issue at all. When you run a return on a security as a function of return on the market, a return on security can be negative, and return on market could also be negative as well. So having a negative value is not an issue at all.
Sir, can you throw some light on weighted least square sometimes to remove the problem of heterozygosity?
The idea there is
you have shown something previously, sir.
This is what I was referring to. So this is this weighted least square version. So what we have come up is that this is something, okay, which we were saying. We run a regression of distance traveled with okay, age, income. Okay, this is what we were running a regression, and we found that my variance of the error term is actually okay directly related to my income. It was supposed to be, if it was homoscedasticity, then sigma square t should have been only sigma square. But no, it's a direct varying from the income level. If that is the case, what you do is, okay, you take this sigma square of the error term, okay, model it expressly. This is one such model. You can also have a model which is something like omega plus alpha, okay, xt. You can have any such variation. Okay, you can have omega plus alpha xt square. Okay, so you can also have log of xt. Okay, but in that case log could be a negative value, so you need to be careful in that case as well. So you can have a different models, okay, but each one is a variance model. Okay, what Engel gave an arch model is also a model which also says that your variance of the error term is omega plus alpha, okay, error term square plus beta into the previous variance term. This is also a variance model as well, okay, which earned on Professor Engel a Nobel Prize for his work on the Gauch model as well. Okay, so each of these models are actually nothing but they are trying to model one or the other way in which the volatility variance of the error term is actually been assessed as a pattern. Okay? So you see a pattern here. The pattern was, in my example, that my error term was directly proportional to the variance. Higher the variance, higher was the higher the income, higher was the variance of the error term. If that is the case, okay, suppose you use this kind of a model, you square root them. Okay, so sigma t is actually sigma times square root of t. This is what it will be. Okay, now you simply take this number, use it as a denominator for the entire equation here. Okay, so here it becomes take only this sigma t on the other side. Okay, so divided by that. So that's what you use it. Okay, and what exactly is you will be obtaining. Your regression is this one, and this section, let me use a black pen here. This section, okay, is 1. This section is 1. This section is again 1. This section is again 1. So what are these? This is nothing but weight, wi. So you run a regression yt, okay, b1 plus b2 x2 plus error term. You don't run a regression on that. You run a regression of w2 t, if you define wt as 1 over square root of xt. Okay, so wt this one, wt here, wt here, and wt here. So use the weighted regression model to estimate its parameter. That's why it was called as weighted least square. Okay, so where you take a weighting mechanism in that case, but you need to be sure about what is the weighting mechanism. Should you use age factor, okay, as a weighting mechanism? Should you use income? Should you use number of kids? Which variable you need to use as a weighting factor? That insight you need to only can come up when you dig it more as to what is actually causing heterozygosity. Okay.
Thank you, sir. Sir, GLS and OLS are both are same or something different are there?
Okay, GLS is one of the special case of GLS is weighted least square. Okay, and you are applying a weighting scheme here. That's why it's called weighted least square or generalized least square. Okay, that's a special case of that. Okay, because you can have various other weighting mechanism as well. So OLS is the simplest one. Running a regression here without any weighting mechanism is OLS. But if you go for WLS, weighted least square, or any other modeling, which you have done it, you are resorting to some sort of a generalized least square.
Sir, how can we know where to what use, sir?
Okay, it's a trial and error. In this, I showed you the graph that it's the income which has been affecting. Okay, the square of the variance of the residual is expanding along with the income. It's not expanding along with the age. It's not expanding along with the number of kids. So this kind of a trial and error, you need to do it yourself. Okay, so as I said, okay, econometrics is not a science. Okay, it's also an art. You need to try various possible combination and permutation and see what is exactly it is causing you.
Sir, if a data set contains a lot of heterozygosity issue, we can use generalized least square method and avoid that problem.
Okay, generalized least square, okay, will involve a weight. So you need to decide on the weight. If you can decide the weight, okay, you can use it. Okay. Otherwise, okay, what the people find it convenient. Okay, they don't want to indulge in this exercise. Whether my variance is a function of income, whether my variance is a function of number of kids or age, I don't want to indulge in that. Okay, I don't have a time and energy for doing that. So what they do is they look for robust estimates. Okay.
Okay, that will automatically. Thank you, sir. It's a good. Thank you. Nicely explained, sir. Delighted.
People been using that. To be cautious about that. So you have a general, what I'm calling as a weighted least square, and you have a heterozygosity consistent. Okay, so two things you need to keep in mind. Okay, when you have a small sample data, okay, only this thing can work. Your heterozygosity consistent or a hack consistent will not work. Okay, so you cannot go for those robust estimate. Okay, the software is not denying anything. Whatever you click it, software will do it. Okay, but the only catch you need to see in that case is, okay, this procedure is only a large sample procedure. That's not a small sample procedure. So you have to go for GLS based procedure when you have a small sample data. When you do not have a large sample data, even if you go for robust standard error, okay, that's not a good way to move forward. However, software will not deny. Software will never say you can't do this. Okay, so software will let you do it. So software is not changing on that case. Okay. Second thing, okay, which you also need to keep in mind. Here you need to be, okay, doing some sort of a modeling. Okay, here you are not supposed to do any modeling. Okay, what do I mean by modeling here? Okay, we are doing some sort of a variance modeling. Here you are not doing any sort of a modeling. Okay, it's all which has been done at the back by the this correction mechanism here as well. But if you do it using the this procedure, heterozygosity consistent estimate or hack consistent estimate procedure which you applied, okay, if you are sure about that, I know that variance is directly impacted by the income. Okay, and given this knowledge, if you still use this HC estimate, okay, so then these estimates are still lesser efficient. Okay, this is a better one. It's a better efficient. Okay, so it's a much better if you have this insight with you that it is the income which is causing the heterozygosity. It's not the number of kids, it's not the age, it is the income which is causing the heterozygosity. If you have this insight, use that insight, build a variance model, a sub model for that, and use it for that. If you use it, then the estimates are a better efficient estimate. Their standard error is a much better than a heterozygosity consistent. Okay, and people, okay, if you're not indulging in that case, okay, then you can opt for your HC estimate. Okay, people have rather, as I was saying, has overly used it or probably abused it to an extent that they don't even think that there is a heterozygosity or not. Apply a robust standard error itself. Okay, so you will find that in many places, those who have been using it day and night, okay, this kind of a regression modeling, they have actually been using only the heterozygosity consistent estimate. They don't have time, money, energy left for doing this itself. Okay. Specialized data will also need a specialized understanding as well. Okay, so it's only you who could got that what has been applicable in your case. Okay. Okay. For example, in the distance travel, okay, I constructed a data, I picked up a data, so chosen the data that it is only the income which has been affecting. Okay, in some other context, which is the variable which will be affecting your the data set? Okay, it is only you who knows about what is the review of literature section. Okay, but don't undermine that itself. That is the where you know about your theory, you know about your aspect. Okay, will able to see what exactly that theoretically able to connect what kind of model is a better model for you. Okay, this is the procedure which I was talking about. Okay, remember that was your HC1 or default rather. Sorry. Okay, that's what it was showing. Okay, I've shared you one Excel sheet, okay, where the correction procedure is actually been implemented. If you are interested, you can go to that itself. The weighting mechanism, use of W, okay, LS, I've also implemented with you as well, okay, and you could obtain those results, okay, alternatively. Okay, given me a choice, which one I will select, okay, given this information that I know it's the income which has been causing, so I'll go for WLS, I will not go for HC estimate, okay, because I get a much better estimates of standard error, okay? Even if I have a sample size of 200, which I had in this case, okay. Okay, so I've talked about the two procedure. I also talked about the relative merits and demerits of both the procedure as well. Okay, now let me come to the next violation, which is your autocorrelation. And as I have said, okay, there is a simultaneous okay correction which you can also opt for that as well. Okay, okay, so what is this assumption? The assumption says that error term for today, okay, I is not related to, there's no zero correlation, there is zero covariance between error term today and error term tomorrow or error term yesterday, okay, any other point in time. Okay, so when you have error terms, okay, along this, okay, any error term with any other error term at different point in time are simply not being correlated. Okay, error term which is with itself, okay, if you compute a covariance of epsilon I with epsilon I, so that covariance is nothing but a variance itself, which was your assumption of heterozygosity. In the case of covariance, okay, error term today versus error term yesterday or tomorrow with I is not equal to J, supposed to be equal to 0. Okay, if that happens, you have no autocorrelation. If that doesn't happen, you have a problem of autocorrelation. Okay, so what is the way in which you can actually judge it? Okay, so again, there's a graphical way as well, which you can use it for this purpose. So what you could do is, okay, you can store residuals, okay, create a residual, store it, okay, and you have okay, tomorrow's error term, okay, and today's error term. Simply take a lag, okay, and prepare a scatter plot. So prepare a scatter diagram of the error term today and error term tomorrow, or error term, okay, today or error term day before, sorry, yesterday. It's one and the same thing. This is T, this is T plus 1. Okay, so with a lag you can construct that. Okay, and if you see no pattern in this case, it's all randomly distributed. It's neither going up, it's not going down, it's not going up and down, it's not going down and up. Okay, it doesn't have anything which is any sort of pattern in that case. Okay, if nothing has been happening, you have absolutely no problem, no autocorrelation problem. Okay, alternatively, there's one more graphical way which can be used. Okay, if you have an error term, you plot an error term here on the y-axis and you plot a time on the x-axis. Okay, as I said, mostly the autocorrelation problem is in the time series. So you put an error term residual and the time, some going up, some going down, there should not be any pattern in that case. Okay, if that happens, that's a problem, that is a situation of no autocorrelation. Okay, as somebody also asked, okay, what is the difference between serial correlation and autocorrelation? Okay, we are using it interchangeably only. Okay, there's not much of a difference between serial. Okay, there's a fine difference, but I don't want to indulge in that itself. You can also opt for cross-sectional autocorrelation in the cross-sectional data set. But 90% cases, over 95% cases, okay, you'll all have a problem of autocorrelation only in a time series data, not in a cross-sectional data. Okay. Then, okay, if there is a autocorrelation, then it could be of two types. It could be positive autocorrelation, it could be negative autocorrelation. So how does a positive correlation autocorrelation looks like? If the error term tomorrow and the error term today, if you plot a scatter plot of that, it shows you an increasing graph. Okay, so if you have an increasing graph in that case, remember, okay, in the earlier graph they were all random pattern. Nothing of and no such pattern was visible in that case. No such pattern was discernible, okay, in that kind of a scatter plot. But when you have, okay, a residual today and residual tomorrow, okay, or residual today and residual previous day t-1, okay, in that graph, if you see some sort of a pattern which is positive one, so you have a situation of positive autocorrelation. Or alternatively, if you plot residual here, okay, and not a previous residual on the y-axis, you put a time on the time versus residual plot. This is residual versus past residual plot. This is residual versus time plot. Okay, if you see in that case, and if you see cyclicity in that pattern, it goes up, it goes down. If you see cyclicity in that case, that's also indicator of a positive autocorrelation. So either this way you get a positive autocorrelation, okay, a picture, or this way you get a positive autocorrelation in that case. Okay, so that's a situation of positive autocorrelation. Alternatively, you can have a situation of negative autocorrelation. What happens in the case of negative autocorrelation? If you plot of residual with the lag of residual itself, and you see a downward sloping pattern. Okay, no random pattern, no upward pattern. If you see a downward sloping pattern in that case, that's an indicator of a negative autocorrelation. Or alternatively, if you plot a residual on the y-axis and time on the x-axis, okay, then you see alternate in sign. Okay, remember, mean of the error term is 0, so it will be hovering around 0 only. Okay, so when you see a positive error term, the next one is negative. This is negative, next one is positive. If this is positive, next one is negative. Then it becomes positive, then it becomes negative, then it becomes positive, then it becomes negative, then positive, then negative, then positive. It alternates in sign. Okay, if that is what has been happening, that's also an indicator of a negative autocorrelation. Okay, so as I said, okay, just let me repeat as a conclusion. If you have a just remove these marks. Okay, if you have random, no pattern, neither increasing nor decreasing, and all these are random, positive, 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 negative, positive, okay, negative, positive. So it changes. Okay, no pattern in that case. Okay, that's a situation of no autocorrelation. In the case of positive autocorrelation, scatter plot will show you an increasing curve, and there will be cyclicity in the error term patterns. That will be indicator of positive autocorrelation. In the case of negative autocorrelation, when you have an error term within error term scatter plot, okay, showing you a downward pattern, or okay, in a error term versus time plot, you have positive followed by negative, negative followed by positive, positive followed by negative. It alternates in sign. That's an indicator of a negative autocorrelation. Okay, so why should I worry about autocorrelation? The autocorrelation has the same problem with that of a heterozygosity as well. Okay, so again, your estimates are linear, estimates are still unbiased, estimates are still consistent. Okay, so you need not worry about if you only need to compute your point estimate, and you must not be computing your confidence interval or the hypothesis testing. If you're not supposed to indulge in any of those, okay, you can simply ignore the problem of autocorrelation as well. But if you want to go for hypothesis testing, okay, then that will be an issue. So your estimates will not be efficient, which in other words means that your estimates of standard error will be wrong. And if standard error is wrong, t statistics values will also be wrong, and p value will also be wrong. And the confidence interval which you construct 95%, okay, lower the higher limit, that will also be wrong. Okay, so you cannot use in for this purpose. Okay, so your output is of no good for hypothesis testing. Okay, and it's also not good for confidence interval construction as well. but it will still be unbiased, still be linear, still be consistent estimate. Okay. Why does autocorrelation arise? For multiple reasons for that. You have omitted variable bias, which is a specification issue. Okay, one of the specification issue. You have inertia in the dependent variable. Dependent variable does not change. Okay, so for example, you look for kerosene prices, okay, which are controlled prices, and you run a regression of kerosene prices with the oil, okay, market prices. Oil, okay, crude oil prices, okay, much more volatile, much more affected by various geopolitical issues. But kerosene prices, okay, is a highly controlled, okay, kind of a prices. So if you have inertia in your dependent variable, that could also result into autocorrelation as well. Okay. Autocorrelation, okay, as I was also saying, it's a more observed in a time series data set. Okay, and they are not observed much in a cross-sectional data set. So whenever you have a time series data set, including a panel data set, because even in the panel as well, you have a time dimension, okay, you are likely to have an autocorrelation problem. Okay. Then how to detect it? One is a graphical way. I already talked about. You can either look for residuals, plot against the residuals with a lag, obviously, or you can have a residual plot against time as well. Okay, both the graph can actually work for you. So situation of no autocorrelation, positive autocorrelation, okay, or negative autocorrelation. Are there any formal tests? Yes, there are formal tests as of that as well. Okay, you have Durbin-Watson statistic, highly used test statistics for autocorrelation detection. You also have the serial correlation LM test as well. So there is also two such tests which are being used. Okay, generally when there is a problem of autocorrelation, with most of financial data, you do have a problem of autocorrelation. Generally, the autocorrelation problem in most of the economic and financial data set is of order 1. Okay, that means error of, as I was saying, okay, in the graph, error of today is dependent upon error of yesterday. Okay, but it could also happen that error of today is dependent upon error of yesterday and also day before yesterday, t-2, or okay, error t-3. It can actually be depend upon not just for the previous lag, but previous to previous, and okay, even beyond that as well. But mostly, most economic series, you will actually find it's of just previous okay, error term. Today's error term is dependent upon the previous error term only. Okay, not the today's error term is dependent upon okay day before yesterday's error term. Okay, this generally is not found. Okay, but I am not saying that that can never be found. That could also be found as well, but generally this is not the case. Okay, generally it is of the just previous day only. Hence, if it is a previous day only, Durbin-Watson statistics does a sufficient job for it. But if you need to check for more than one lag, okay, so not just previous, but okay, previous to previous day, day before yesterday, okay, or 2 days yesterday, then in those cases, okay, it's better to go for serial correlation LM test. Okay, don't use Durbin-Watson test. Durbin-Watson test is okay, is a much better test for a first order autocorrelation problem. This is called first order, when your today's error term is dependent upon yesterday's error term only. Okay, only with one lag, not more than one lag. Okay, so Durbin-Watson is a test statistics only for one order. Okay, it's crudely, as a rule of thumb, its value should be hovering around 2. Okay, when you Durbin-Watson statistics value is 2, okay, that means autocorrelation is 0. If its value is closer towards 1, not 1, autocorrelation in your data, and if its value is towards 4, then there's a negative autocorrelation in the data. That means when you compute a DW statistics, if your DW is closer towards the value 2, you have no problem of autocorrelation. Okay, everything is right. Go ahead and interpret your result. Use for standard error estimate. Use it for confidence interval, hypothesis testing. Go ahead in that case. If your DW statistics is closer towards 0, you have a positive autocorrelation problem in your data set. Okay, if your DW statistics is equal to 4, then you have a negative autocorrelation okay, problem in your data set. Okay, so if there is no problem, okay, everything is fine, you are need not worry about it. But when you have a positive and not negative problem, okay, autocorrelation in your data set, okay, then again you have two choices. Okay, what are those two choices? Same which I talked about in heterozygosity case as well. Okay, so whether there is a positive autocorrelation problem or whether there is a negative autocorrelation problem. So either you can use this, okay, in your model. So you get your ET is row times or correlation time ET minus 1. Okay, so you use this as an extra information, use it in your OLS estimate, okay, which gives you nothing but your GLS estimate only, okay, and you get your better estimates in that case, okay, which has been modeling this kind of an procedure itself. Alternatively, you can go for HACS, consistent estimate as well, which is your robust one. So same two choices which you were having in heterozygosity case, you also have it here as well. So either you can opt for GLS, okay, procedure, or you can opt for, okay, heterozygosity, the autocorrelation consistent estimate. It's a robust estimate. So these are the two choices which still remains with you, okay, while trying to model it your autocorrelation problem. Okay. Okay, so how to implement it in a okay, with a data set. Okay, so let me just show it to you. Okay, so you are also having other as Bruce-Godfrey serial correlation LM test. So you can also use, okay, but use it when you have more than order 1 correlation. Okay, if it is of order 1, okay, you can safely use your Durbin-Watson statistics for that as well. Okay. If you want to model it, GLS procedure, which has been suggested by Cochrane-Orkut procedure, okay, which is to run regression first. Firstly, you run a regression, obtain residual, then you run second regression with the residual itself. Residual with the lag of residual, you obtain your R, which is your estimate of population correlation, okay, and then you make changes and then okay. Run a GLS procedure on that itself. Okay, how we are doing that? Okay, that's what you can see with the help of an example. There is an example on sugarcane prices and area under cultivation. Okay, it's been taken from book which is Hill Griffith and okay, and the Lim's book as well. It's a very good book. Okay, you can refer to that for some of these understanding on heterozygosity consistent estimate itself. Gujarati has more okay of a description on GLS, okay, while your Hill Griffith and Lim's text has more discussion on your heterozygosity consistent estimate. Okay, so you can use that. Okay, so idea here is that how does sugarcane prices affect the area under cultivation? So we have been given certain observation, area under cultivation of sugarcane in terms of acres, so 29 acres, 71 acres, or 42 acres, and the price of the sugarcane per okay, quintal or per ton, okay, which has been given to us. Okay. The model which is to be run is the log of the area under cultivation is a function of log of prices itself. Okay, so you want to run this kind of a model. So is the sugarcane prices affects the area under cultivation? If the sugarcane prices are being higher, okay, will that be a lower number? Okay, 1 second. Okay, so that's the kind of model which you are having, whether the sugarcane prices do affect the area under cultivation. Okay, so we can run a regression on that, check whether there is a autocorrelation problem and make correction accordingly. Okay, okay, so let me just use it. Okay, so let me clear my data first and import an Excel sheet, which is sugarcane data. Okay, so let me just import a sugarcane data. Let me just firstly have a view. What is there? Okay, so this is only have the data while your exercise has both. Okay. So let me just take that data exercise, open it, import first as this. Data range is 1 to 80. 80. 1 to 1 to A, B, C, D, F, G, up to G only. Okay, let me import this data and let me have a view of the data itself. Okay, so there is no brownish, reddish number here. So that means all been imported as a number. Nothing has been imported as a string. You have area under cultivation. You have price of the same data. And log of area, log of price has also been there. Okay, and transform variable is also been picked up from the Excel. Okay, which has already been shared with you all. Okay, they all been there. What is there in the data is in terms of because our model is in terms of log format only, so it gives you area under cultivation and sugarcane prices. Then log of the area, okay, it's just a ln function applied in Excel, okay, and then there's a transformed series as well. So what we are basically doing in this case is all these transform series is also being imported here. Okay, so let me first run a regression. Go to statistics, linear regression, and opt for log of area as my dependent variable and log of price as my independent variable. Okay. And already constant has been there, so I'm not putting anything on that. I simply run a regression on this. Okay, so I got this one. Okay, but before that, I also need to do something. Let me define this as my time series. So do I have this as time series observation? Define it as my time series. Then run a regression on this. Okay, so I get my regression results here, okay, which is based on that log of price. Okay, log of area is my dependent variable and log of price is my independent variable. So log of area under cultivation is equal to alpha plus beta log of price plus the error term. That's a model which I have run it. Okay, so I get a constant which is 6.11 and I get a beta which is 0.97. Okay, how you interpret this beta? Because it's in terms of log model, so this beta is in terms of elasticity. So you have elasticity of area with respect to price, which is less than 1. So it's slightly unit elastic. It is approximately 0.97. So if your prices goes up by 1%, area under cultivation also goes up slightly 1% itself. Okay, or probably saying if your prices of sugarcane goes up by 10%, then the area under cultivation goes up by 9.7%. So approximately 10%, but 9.7% is what you have been having it here. So you will be having this kind of interpretation for these values. But before you actually, if your task is to estimate this and nothing else, whether they are significant or not, okay, whether you have what is the lower limit of this elasticity, what is the higher limit of this elasticity, okay, if you want to comment on that, okay, then you need to be worrying about whether your data suffers from the autocorrelation problem or not. Okay, for doing that, okay, you can use formal tests as well. Okay, so what are your formal tests of that? Okay, somebody asked, okay, why we take log? Okay, there are multiple reasons for taking a log itself. Okay, there's no one single reason. Remember, I said, okay, at times taking a log can make your residuals follow normal distribution. That's a one reason, but that's not the only reason. By taking a log, you can also handle at times heterozygosity as well, because transformation can also help you at times in the heterozygosity. If your data is slightly skewed, but not okay, acutely skewed, if your data is having some amount of skewness, your dependent variable is some okay, slightly skewed, then again taking a log can also make correction for your skewness as well in your data set. At times you also take a log for okay, interpreting it in terms of returns rather than interpreting it in terms of okay, the absolute value. So you want to talk about growth rate in GDP. You don't want to talk about the GDP per se. Another reason for taking this could be that you are more interested in estimating elasticity, because here this is estimate of elasticity. Okay, so by taking a log, that could also help you solve for elasticity. So there's no one single reason. There are multiple reasons of taking a log. Okay, in for the data set. Okay, working in that context. Okay, depend upon the context. There's no generic panacea for all solution. Okay, coming from the log as well. We do check for heterozygosity first, or we apply tests like T, ANOVA, correlation regression to test for the hypothesis. Okay, that depends upon your heterozygosity is an issue only with the regression. It has no other problem with the other tests. A simple T test, okay, we have been looking for those okay, level multiple need to be worrying about that heterozygosity. It's embedded in that case as well. Okay. So whenever you look for heterozygosity, you need to look for heterozygosity whenever you conduct your hypothesis testing, the confidence interval construction. Okay, so let me go for checking of autocorrelation. So I go to statistics, I post estimation. You have a test for to Pagan, Godfrey test for first order serial correlation. So you can opt for Dublin-Watson D statistics, launch it, okay, and this is for the time series only. So I'll go for it, okay, and you have DW statistics. Okay, so here you are getting a value which is okay 1.29. It should be closer towards 2. If it is not closer toward 2, okay, it will vary from 0 to 4. If it is somewhere between the closer to 2, no autocorrelation. If it is closer towards 0, okay, in this case it is 1.29, okay. So there is chances of positive autocorrelation. If it is closer toward 4, let's say it is 3.85, okay, then there are chances of negative autocorrelation. Here there is okay a case for a positive autocorrelation. Okay, so here when you actually look for DW test statistics, it's a peculiar test statistics, okay, in the sense that you don't have a clear-cut case of what has been referred as one second. Okay, so I think I don't have that. So what generally happens in this case is, okay, you don't have one single spectrum. So there is somewhere, generally what happens when you have your acceptance and rejection region, so they are clear cut. Okay, this is your acceptance region, acceptance of null, and this is your rejection region. Okay, rejection of the null. But in the case of Durbin-Watson statistics, what happens is that you have a distribution. So you have 1, 2, 3, 4, 5 section. Okay, middle one is your acceptance of null. The extreme left is your rejection of null. The extreme right is also the rejection of null. But in between, you also have a region which is of indifference. Okay, and that is actually given by two statistics in the Durbin-Watson case. Okay, so in your Durbin-Watson, it is 1.45 and 44 and 1.54. So if your test statistics falls in between this region, so you are in a indecision mode. You can neither accept the null nor you can reject the null. Okay, that's a peculiarity with the Durbin-Watson statistics. Okay, so given your observation which you are having, we were getting a value which was 1.29. Okay, it doesn't fall between 1.44 and 1.54. So it's not in the indecision zone. It's clearly in the rejection zone. So you are having 1.29. So there is a chance of a positive autocorrelation in your data set. Okay, so if you have positive autocorrelation in your data set, then what you could do for that. Okay, so again, either you can opt for the GLS procedure or you can opt for the HSE estimate. Okay, in the case of GLS procedure, okay, what we did was we obtained these number. We were getting 1.29, okay, as our Durbin-Watson statistics. We get a value of okay, so it is less than 1.39. So you are 1.29 is less than 1.39. Obviously, that's a clear indication that you have a problem of positive autocorrelation. Okay, and if you have positive autocorrelation problem, then okay, there are two things which you could do. Either you go for GLS, compute, store the residual, run a regression of this correlation coefficient, okay, and use it to transfer data. Okay. How you do a transformation, that's been specified here. 1 second. Okay. But once you go for this estimate of the rho, okay, you do a transformation. Generally, it means that the transform variable of area and transform variable of price. Okay, what you do transformation? You take the area which you estimated, okay, and the lag of for the previous day's area itself. Okay, this is a transformation which you do it for second observation, third observation, fourth, fifth, okay, till all the observation. You apply this kind of a transformation. Why not? You cannot. Why you can't apply for the first y1? You will have y1 minus correlation times. Why not? But there is no previous term except the first one. Okay, so for the first one you go for this kind of a transformation. Only for first observation you make this transformation, and for rest of it you make this kind of a transformation. Okay, these transformations are already been done in the Excel sheet. Okay, so the Excel which I was having. Okay, these log A star and log P star, they already have these transformation which is being conducted. Finally, what you need to be doing in that case, you run a regression not on the original series, you run a regression on transformed series. So you opt for log A star as your dependent variable, and you opt for log P star as your independent variable. You don't go for the log P. Okay, you run a regression and you interpret this thing. Okay, this is your correct estimate of your elasticity. It's not 0.97. It's slightly different in that case. It's coming up as 0.55. Okay, so you will be interpreting this one rather than the original one. Okay, you should not be interpreting that. You should be interpreting this one if you are having autocorrelation problem in your data set. Okay? So you need to be making either a GLS transformation, or you can opt for your HSE transformation as well. Let me see if the HSE is also in the same procedure. Sorry, it was in statistics, linear regression, HC robust. So robust, cluster robust. I really don't know where exactly I can find that. This is at C3 only. Okay, there must be HAC, okay, consistent estimate as well. In the presence of autocorrelation, okay, you can opt for that only. Okay, so there must be an HAC. I really need to search for it. Probably how you can implement that in Stata. Okay, I really need to search. Okay, and I'll get back to you accordingly.
In heteroscedasticity also you use that, na? HAC you are talking of.
Yes, okay. It's a combined rectification for both heteroscedasticity as well as autocorrelation, but that is an HAC procedure.
Not but only Robert standard error is correction for heteroscedasticity.
Yeah, so if you only get your default or HC1 or HC2 or HC3, for example, just in an effort to show for HAC, I run it HC3. Okay, that's just for the heteroscedasticity only, not an autocorrelation adjusted. Okay.
But there are 3 options is showing, sir. Which one we know? How can we know?
That's what is an art in that case. Okay, probably what is really been applicable, but I'll suggest that probably you refer to book by Hill, Griffith, and Lim.
Griffith,
that
econometrics.
Yeah, so principle of econometrics by Hill, Griffith, and Lim have more discussion on these heteroscedasticity.
Okay.
We'll get some aspects on that.
No, sir. The problem is that I have used some regression. Then there are comments comes from reviewer. You used some robust methodology, so I don't understand that. I think perhaps
that's the same thing. That's a robust. Whenever they say robust,
standard error.
If it is in the context of regression, robust means these HC consistent only.
Yes.
However, robust also has some other meaning as well. Okay? When you say use robust methodology,
yes,
then that it basically means you use 3-4 methodology to confirm the same thing.
Yes. Okay.
Any other question? Any other doubt? Any other question? Any other doubt to anyone? We discuss this and all regression assumptions and everything in a course which spans for at least a semester. Okay, I just try to synthesize that into a 3-hour lecture for you. Okay, so I don't know how much justification I could do with that. Okay, but that's what I tried my best for putting at least key concepts to be discussed for our purpose. Anyone having any other question, any other doubt?
Yes, sir, I have one question. I am Sunita Ramchandani, but it is related to my data only. So Like if this platform allows, I can question here, or if it is possible, you can provide your contact number so I can ask later on. I mean, as per your convenience.
I'll share my details with.
Yeah, sure, sir. Thank you so much. Please share your details because I really have some doubt. I mean, I am in midway of data analysis, but I have few queries. So that's why I'm attending especially this econometrics workshop. I am working on economics topic only, my PhD topic, and I really want to do some data analysis, but there is some confusion. So I just wanted to clear it out. So if you can share your details, I'll be really, it will be really grateful to me.
I'll share that as well. Any other question to any other participant?
I have one question actually. You have said that transforming the variables, and regressing the models on the transform variables, will it remove the problem of heterozygosity and autocorrelation?
Yes, that's the way in which these are been suggested. The transformation is of a specific type only. So when I talk about transformation, for example, in this case, the transformation is what has been suggested by the Cochrane and Orkut procedure. So this transformation is suggested to remove the problem of autocorrelation. Not necessarily heterozygosity. So at times having a log transformation of the variable can also remove the problem of heterozygosity as well. But log transformation can remove the problem of autocorrelation. I'm not saying that. So there is no general panacea. I can only say that there is a transformation which might help sometime, but not in all the time. But transformation do help in removing some of these problems sometime, but not in all the times.
All right, thank you.
Any other question? Any other doubt to anyone?
I think so. No other question.
Okay, then we can wind up for the day.
Yeah. Narayan sir, that's it from your side or anything else?
Thank you. That's all from my side. Thank you.
Okay. So, dear participants, do you have any question or doubt or any view about the session? You can share quickly.
Any quick feedback if anyone you have?
We have a formal feedback link, but anything else, informal feedback, if you want to share, you can.
Yes, sir, I would like to share.
Yeah, Sunita.
Yeah, this is really excellent workshop I have ever attended, because I have seen and I have attended many other workshops where the practical exposure is given by the expert, but the way Narayan sir was explaining each and everything, like first he was giving the explanation of all the techniques or what should we use, and after that he was applying through this data, and he was explaining each and everything. So the way he has explained all the concepts are really very like impressive and knowledgeable. I mean, I was able to get each and everything from this workshop. So thank you so much, sir, for making it very easy and understandable for us. Thank you so much.
Thank you, ma'am, for your words. Anything else? Okay, so quickly, I would like to summarize the session. Narayan ji has covered first about the regression analysis, then he has covered in detail about the violation of assumptions. He has explained one by one all the assumptions with actual data sheet and Stata. Then he has explained the issues related to heterozygosity, homoscedasticity. Then sir has also covered how to deduct autocorrelation. Sir has also explained in detail OLS estimation, how to work in a Stata, the commands related to stata, interpretation of the results, sir has explained in detail. Thank you very much, Narayan sir. The most important, thank you for accepting our invitation at the last moment. Just 2 days ago, we have approached you and you have accepted our invitation, and you have covered the topic which we have assigned you, and you have justice with that topic you have explained in detail. So thank you very much for sharing your knowledge with us. Thank you very much sharing your time with us. Thank you very much from the bottom of the heart. And we hope that this association would be continue, and in future, again, we will invite you on this kind of the more platforms, and I hope more participants would be benefited. Thank you very much, sir. Thank you.
Thank you. Thank you, Rajinji.
I would be happy, sir, if you can share your PPT with us so we can forward to all the participants. If there is no issue, if you don't mind it.
I'll mail it to you. Okay.
Surely.
Sure.
Dear participants, I can understand this econometrics workshop. Hands-on practice is very, very important, and it is not possible parallelly we can do all this exercise. So therefore, with that objective to improve your hands-on practices, these sessions are live streaming on the YouTube, and this is also recorded. So if you want to see the recording of these sessions, you can check it our YouTube channel, IBMR IPS Academy. On this YouTube channel, this recording is there. You can anytime access these recordings, and you can do it hands-on practices. In case you have any doubt, you can check it on YouTube. So somebody was asking whether this recording will be forwarded you or not. So this is for your information. These recordings are uploaded on our IBMR IPS Academy YouTube channel, which you can search on YouTube, and you will find out all these recordings. So you can access these recordings. Narayan sir, we will also forward you the link of these recordings also.
Thank you, Sanjeev.
That's it for the day. Tomorrow again, at sharp 10 o'clock, we will start the session. Our first speaker would be Dr. Karunesh Saxena. He is the professor at FMS Mohanlal Sukhadia University, Udaipur, and he will cover the topic time series analysis as well as the unit root and stationarity issue in the econometrics. So that's it for the day. See you again tomorrow morning. Okay.
Thank you all.
Thank you very much, Narayan sir, once again.
Thanks, Sanjeev.